It's Rudi from Eindhoven. We'll talk about bounds on number of cells in the Dressian, right? I don't know what it is, but
Thank you, Sang-il. Also, thanks to the organizer for inviting me. Cells of the Dressian. So indulge me, and who knows what a valuated matroid is? Okay, and who knows what a Dressian of a matroid is? Yeah, I need to explain this before we can. So I have slides explaining this. Okay, I will not dwell on the definition of a matroid, but this here is the definition of a valuation. So sadly, these valuations are not the same things as what Benjamin was talking about just now. They're not values you assign to polytopes. They're a list of values you assign to the basis of your matroid. And these values are not arbitrary. They need to satisfy this inequality. And you will recognize sort of a quantitative version of the symmetric base exchange axiom when you come from matroid theory. So then the Dressian of a matroid then would be all the possible valuations of that matroid. And I will, most of the time, investigate the Dressian of a uniform matroid, so I'll abbreviate this to that. So these are not my definitions. The definition of evaluation is due to Dress and Wenzel. They were sort of investigating a framework that nowadays would be Baker-Bowler theory. They were considering the whole oriented matroid framework and the various cryptomorphisms, and we're looking to see whether there are other structures like that. So evaluation is really a close analog of an orientation of a matroid. The name Dressian then comes from a paper by these four authors, Herman, Jensen, Josvik, and Sturmfels. They were doing tropical geometry. So in tropical geometry, evaluation is viewed as the Plücke coordinates of a tropical linear space. And this axiom is like a tropicalized version of the Grassmann-Plücke equations. And yeah, when you do tropical geometry, your entire world becomes cell complexes. So they recognize that this set of valuations is sort of naturally is a polyhedral complex. It's the union of cones. And my job today is to make bounds on the number of cells of this polyhedral complex. So I will now explain in a bit more detail how these cells look like. I mean, how would you count them if you don't know? So my original perspective was not tropical geometry. So I was more thinking about the combinatorial type of evaluations. So this definition here really has combinatorial aspects, right? For each B, B prime, and E, you can choose an F. So evaluation has sort of a combinatorial characteristic, which is simply the list of all tuples B, B prime, E, F, for which this inequality holds. And then, the geometry comes in, because if you then consider all the valuations that have the same combinatorial type, well, that's evidently a cone. Right? Because you're then asking for valuations that satisfy this system of linear equations that you just assembled. So it turns out that actually the exact same information is captured if you look at the tuples where the difference between the bases is 2 and you have equality in this inequality. And so what I'm saying here is that if you know this list, then you know this one, and if you know this one, you know that one, right? There's a one-to-one correspondence. And that's not completely trivial, right? What goes in there is a theorem of Dress and Wenzel that says that this definition of evaluation is equivalent to the one where you restrict yourself to bases at a distance 2. And then, that's most of the work. From then on, it's sort of an analysis of pairs of bases that are very close. Right? So I won't dwell on this, it's not my work. But this definition I like more because it involves equations and also the tuples that you have here are not so numerous. So you choose your equations from a not too big set, and I'll be needing this. So that's how I choose my definition of combinatorial type. So now the Dressian is partitioned into equivalence classes, right? And these equivalence classes will be my cells. They are exactly, so the cell that a particular valuation is in is just all the other valuations that have the same combinatorial type. And as noted, these cells are cones. They're open cones or half open cones. You can't quite see from what I said. They're actually open cones. Clear so far? Okay. So now, what I'm studying is the number of cells. So simply this count of the number of different equivalence classes. And I will also, when finding my bound, it turned out to rely on a good bound on the dimension, so I'll first investigate that. Right, so the dimension of the Dressian is simply the maximum dimension of any cell. So what will turn out to be very useful in this investigation is that the linear hull of a cell actually determines the cell uniquely. And that is because, well, if you know the combinatorial type, then you know the cell, simply because the cell is defined from the combinatorial type. Now then, if you know the cell, you clearly know its linear hull. But if you then want to recover the combinatorial type, you just look at any vector in that linear hull in general position, and it'll simply tell you which of the equations are satisfied. So at the crucial moment, I'll always pass through these linear spaces because they're linear spaces and they're easier to work with. So don't worry when this happens. So because of this, it won't affect the count, right? If I pass from cells to linear spaces, I have the same number of linear spaces, and clearly taking linear hull also won't affect the dimension. So here's what was already known about these dimension and numbers. So this sort of covers the situation in rank 2. There is a way to make valuations of uniform matroids of rank 2. And what you do is you make a tree with leaves L and some length functions on the edges. And then for the value of a pair of leaves, you take minus the L length of the path from A to B in T. Now that turns out to give you a valuation. And that is in fact a sort of a generic way to do it. Any valuation in rank 2, in a way, comes from this, modulo minor tweaks. And what then determines the cell of valuation is just the topology of the tree. So now, when I want to know the dimension of a cell, well, what's the freedom that you have? Well, the dimension will be determined by the number of places where you can choose a value here. So that's the number of edges of the tree. So that's 2n minus 3 at most for a tree with n leaves. And the number of cells will be the number of trees with n leaves. Well, I just learned that Cayley has a formula for that, so I will put that in my paper. But this is a reasonable upper bound for that number of trees. So in general, well, there's lower bounds that come from a construction. So if you have any matroid of rank R, you can turn this into a valuation of the uniform matroid. By this construction, you just take for the value of a basis, the rank of the matroid n minus the rank of that in n of that set B, right? So I say basis of the uniform matroid, but it's just an arbitrary R set for the matroid n, so it could have any rank, right? That gives you a matroid valuation. And it so happens that it's actually very hard for two matroids on the same ground set to give you a valuation, two valuations that are in the same cell. The combinatorial type is going to very quickly differ, and this is exactly true for sparse paving matroids on at least 5 elements. When they're different, they give you inequivalent valuations. And so that then gives you a lower bound on the number of valuations, because, well, it'll be at least the number of sparse paving matroids, and we know lower bounds for that. The dimension turns out to be, well, the maximum number of circuit hyperplanes, which is the same value. So I'm going to try and find upper bounds for these numbers in general. And as you can see, they're more or less the binomial coefficients times something. So in this bounds I make, I'll usually compare the dimension with the binomial coefficient and find some upper bound, and hopefully that upper bound goes to 0 as n goes to infinity, right? Then I'm doing well. Okay. So the theorem about dimension that I have says that if r and t are two numbers and t is lower than r, so then the dimension of the Dressian compared to this binomial coefficient can never be greater than the same fraction in lower rank t. And so I will tell you how I do this, but that gives you a very nice bound on the dimension, because you can just plug in any bound you know for some fixed low rank. So we could plug in the bound we know for in rank 2 that comes from trees. But in fact, there's a different bound in rank 3 that gives you slightly better values. This one depends on the spread of the matroid polytope decomposition induced by the valuation. But it's slightly better, and it just gives you this general bound on the dimension. So for the number of matroids, or the number of cells, I find, well, again, a similar formula, but now there's this C log n at the end that I would prefer not to have, but it's simply what comes out of the method. And again, using a good bound in fixed low rank, you can now make a bound on the number of cells in general, which is not too awful, right? We had the lower bound 1 over n for this, and now here we had C log n squared over n. Okay, so how do these proofs go? I started at 40, yeah? Okay. Okay, so the statements I have, they look a lot like a similar theorem I have for the number of matroids. And the way we showed this, so this is an old theorem, is to consider all, we want to count matroids, and so we make an encoding of these matroids. We say, look, if I ask you to reconstruct a matroid from all its minors in fixed rank T, you'll be able to do it, right? Because if you want to know if a given R set is a basis, you just go to a minor by contracting a subset of that R set, and then there is a basis in the minor if and only if that thing was a basis. So you'll be able to reconstruct this thing, and that already gives you a bound which is somewhat poor, right? You can never have more matroids than the number of matroids in one minor of rank 3 and another, and so it's then this value to the power the number of R minus T sets from E, right? So that gives you a reasonable bound. It actually gives you this statement, but times R choose T. And of course, this encoding that I made was awfully redundant, right? If I wanted to know about a basis, I could pick any subset to see whether it is a basis. So I need to do something about redundancy. And what helps, so this is babble about entropy, but this is just a technical tool that in the end helps you to get rid of the redundancy. You make a random variable that takes value in the base sets of random matroids, and then you create these derived random variables, and now you know something about the relation between these numbers and the entropy, and then there is a lemma, Shearer's lemma, that will give you a relation between entropies of derived variables and your original entropy. And this 1 over k is exactly what you need to get rid of the vector r choose t in this theorem. So we can do something similar for dimension. First off, this idea of contraction also works for evaluated matroids. If you make a contraction of a evaluated matroid, you're essentially restricting yourself to the values of the bases that occur in a minor. So, geometrically speaking, a contraction is just coordinate projection. You project on the coordinates, which are all the R sets that contain your set S. And now, the key thing about cells of the Dressian is when you project them down, when you make a coordinate projection of a cell, it'll land inside a cell of the Dressian of the contracted matroid. So, in particular, the dimension of this projected object is going to be bounded by the dimension of this. And now what you need is to make bounds on the dimension of a cell D in terms of dimensions of projections. And it turns out you have exactly this. It's not Shearer's lemma, but I can hardly believe that it's not, because it's really the exact same statement, except that now your entropies turned into dimension, and entropies of derived variable are dimension of projections. I can't derive it, but I can recycle the proof. In Shearer's lemma, you need that a certain function is submodular, and here you need that the function that takes a subset of x to the dimension of the projected space is submodular. Well, that is submodular. That is just the rank function of a linear matroid that comes from this subspace L. So that makes the proof tick. And now you do the obvious thing to prove the theorem. You take a cell, you go to its linear hull, you consider that the dimension of the projections are bounded by this dimension here, and then you apply this lemma. And yeah, again, you take away this 1 over k factor to get rid of the redundancy. Okay, so for counting the cells, I also need a trick that I learned when counting matroids. One problem was that, you have this large class of sparse paving matroids, and a good method for counting matroids also has to count those, right? Because they're a subclass. So it turns out that sparse paving matroids really are in one-to-one correspondence with stable sets of a certain graph, the Johnson graph. And in the end, we found that the best way to bound these was by the container method. So in a nutshell, a container for the set of stable sets in a graph is a set of subsets of the vertices, so that each stable set is contained in one of these vertex sets. And then qualitatively, if this set C, if this container has not too many elements and each subset is not too big, that gives you an upper bound on the number of stable sets. Now, the method that creates containers for sets of stable sets works if you have supersaturation in your graph, which is the statement that large subsets of vertices will have many edges in a precise way. But I'm not doing it precisely here. And so, so if G has supersaturation, then you can find a good container and hence a good bound. So we'd like to repeat this now, not for stable sets in graphs, but for sets of linear subspaces of a space. I planned this much better than I executed this. So, a container for a set of linear subspaces, well, is itself a set of linear subspaces, and each subspace in L is contained in one of these subspaces in C. So that's a container. So what is a good container? Well, you want not too many elements in your container, and each element should not be too big. Well, not too big means not have a high dimension. So this is technically expressed as saying that it's an alpha-beta container. So the beta controls the number of elements in the container, and the alpha controls the dimension of each element. And yeah, I use this way of doing it. I make them relative to the cardinality of the ground set X in this statement. So now my next lemma is a bit terrible, but roughly speaking it says that if all projections have a good container, then the entire thing has a good container, right? When I say all projections, I mean all projections that are pointed out by an exact K-cover. So this is the same context as Shearer's lemma and this lemma about L. Oh, I need to hurry up. Okay. So indeed this is saying that when you have an alpha-beta container in each of these projections, you can make an alpha-prime, beta-prime container for the whole thing. And then, well, what is used as supersaturation effect is now this not Shearer's lemma that I had before. So I won't go to this proof, but you do more or less the obvious thing. You take all the linear hulls of your cells, then use that you have a good container for a projection. In essence, you use the Dressian of the contracted matroid to get this container, and then you apply your lemma, and then you count. So now, yeah, so this is altogether the theorem that we have. We have a lower bound and an upper bound. It's not so bad for the dimension. I think the truth is probably that the dimension is more or less the independence number of a Johnson graph. And you can probably prove this if you can make good bounds in low rank. If you make good bounds in low rank T, I don't have the best bounds, but that'll work. Yeah, and similar for the count. That is a bit worse. This log n squared, it's not right. But really my subspace container lemma is still a bit of a blunt instrument. It's sort of the first iteration. Surely there's better lemmas. And again, I think that the count is more or less equal to well, the count of sparse paving matroids. So that was it. Thank you.
Thank you. Any questions?
So you built kind of a subspace analog of the container method. Can you use it to count Q matroids?
Can I use it to count Q matroids? Well, you can count numbers of subspaces. So you would be able to count numbers of bases in them, right? If you apply it directly. But you would probably need to tweak it quite a bit before it becomes something that counts the number of Q matroids itself.
I mean, if you adapt your techniques that worked for matroids with this subspace container method.
Well, if I wanted to count Q matroids, there's probably an excellent way to do this, and it wouldn't be this. right? I would count essential flats, or I would,
All right. Any other questions?
Is your last conjecture implies the conjecture about the almost all, I mean, the density of the paving matroids are 1 or the other way around?
Sorry, what is the question again?
Does your conjecture, this conjecture implies the conjecture about the density of the sparse paving matroid is 1 or not?
Oh, well, on a logarithmic scale, you mean? Huh? Well, so this construction that takes matroids to valuations, so I said it's nearly true that all pairs of different matroids land in different cells. And you can probably make this precise. I mean, if you look at the matroid polytope decomposition, then actually of that valuation, you actually get the matroid back. So it's rather hard to get two valuations that have the same type. So if you make this a bit more precise, then this conjecture actually implies that, because then log of number of matroids would be more or less in between these two values.
All right. Let's thank the speaker again. Yeah.